Hello, good afternoon again. I'm between the coffee break and you. So I want to just make and transfer one idea. So first of all, to say that we are very happy to be here. So we are with 5 colleagues from the Institute. They come here to join forces with India in fighting the global climate change. And what motivates us is that if we would find in the Institute a trick that would save 6% of the CO2 output of Germany, and if we could convince the Indian colleagues to somehow adopt this idea, it would make a 100% change normalized to German CO2 output for the country. Yeah? So there's a very strong motivation. Let me say one thing. This morning, Thomas Ackermann told us that we should somehow have an open source modeling algorithm culture. And I think it's exactly this thing that I want to talk about it, because I think if we do this, we will have more reliant results. If we have a convergence of algorithms, the accuracy would increase. And in the end, I would like to ask you that how can we somehow form a network that does exactly that joins algorithms, checks the methodologies, and so forth. As an institute, we are doing this, consulting not only the public, the ministries, and the industry on all this issue of system transformation. And the title of my talk is about rooftop PV, but I want to take that as an example of what quantitative analysis could do, and I want to give it a, let's say, qualitative way. I'm not presenting too much numbers, I hope. As an institute, we are part of the Fraunhofer Society, which is Germany's largest society for applied research. We are 300 people out of 24,000 employees. The institutes are distributed all over the country. And we are in Kassel, which is a small city right in the center of the country. So you saw this picture before. We had a tremendous growth of photovoltaics in the last 2 decades. And there were many people who said this was exponential growth. But the character of exponential growth is that while it is exponentially growing, you don't observe it. And when you start to observe it, and there are so many counter forces active, that slows down this growth to, let's say, linear at best, or sometimes slows it down completely. And you see this in this chart because below in blue, you see the gradient, so the installation rate each year. And you see that it had a maximum of over 7 gigawatts per year. And we decrease it to something like 2 or 1. And you see that in the yellow curve, which is the cumulated power, that we are not following an exponential anymore, but we are saturating in a nice S-shaped curve. So you may ask, is that okay for Germany? So we are stopping somewhere between 40 and 50 gigawatts. And that, of course, depends on the target. So I will spend a little time of how do we calculate a solid target. So I can say here we are short by a factor of 5. So what has happened, and what are the obstacles here? And the obstacles are, in fact, in this question of integration. And integration has many aspects, as we learned today. So it's economic, but it's also technical. And in my talk, I want to talk about the technical side of the integration and concentrate on one specific issue. And that's the question, is there a meaningful ratio between rooftop PV and free field PV plants? And you see 2 charts here. On the left is the annual installation of PV power, and in red you see the rooftop PV. So that's what initiated the growth in the beginning. So there were all these private investors jumping on this bandwagon, and we had 95% of rooftop PV. Then later the legislation was changed in favor of free field PV, and you see that in the blue bars, that increased quite a lot. And then again, legislation stepped on the brake, and we came down now to a level, let's say 25% of large installations. if you see that in cumulated numbers, you see that somehow we are saturating with this ratio. So the question that I want to put out here, can we somehow gauge what would be an optimal ratio between rooftop and PV, meaning to say more centralized high voltage installations and more decentralized low voltage installations? And in figuring that out, we need two characteristic figures. So first of which is the total installation that we are targeting at, and the second is the ratio between photovoltaics and other renewable sources, prominently the wind. So here's a little formula, which is the residuum power, which is in this agreement here, the difference between the load power and a mixture between PV and wind. So here we have a little factor alpha, that is a tuning factor that can shift it back and forth. The normalization is such that the maximum installation would be able to feed the consumption alone. So one way to calculate an optimal mix, an optimal alpha here, is to minimize the standard deviation of this residuum. Let's call it a residuum signal. Yeah? So this is somehow equivalent to reducing the infrastructures of balancing power and storage. So this is this magic residuum power that you all know. In this convention, the red fractions are the deficits, and the blue are the surplus or the excess power. And you see here that if you integrate that with your eyes, that that's much more blue than red, and the ratio between that should be larger than the return efficiency of the storage system, because you have to harvest the excess and later put it into the deficit. And of course, you can learn a lot out of the signal if you see that there are these very spiky day-by-day variations, and then are these longer stretches which correspond to wind power, mostly where you have droughts and excess wind. So this is the discussion about this alpha, this ratio. Now we have the discussion of what is the target value, where do we have to go? And this is all a question about primary energy and end energy. So we compiled our needed end energy in the year 2050, and that encompasses all sectors of heating, electricity, industry, and traffic, public transport, but also non-energetic consumption. And this is all in end energy, and this here in this graph is projected on the electricity. So not all of the end energy in the end is created by electricity, but somehow it is levered, because in Germany heat production is important, and by using a heat pump we can take environmental energy and lever it by electricity to yield more end energy in this way. So we come up with a magic number of 1,000 terawatt hours for our country. I'm sorry for using absolute numbers here, so I want to, of course, to get into discussion with the Indian case, and then, of course, we have to use more normalized figures to understand where we are. Now, if we use such an end energy figure, and we use our alpha that we have determined beforehand, we get a ratio between photovoltaics mostly and wind. There's little bimix of bioenergy, which is not so important here. And you see that the ratio energy-wise is 1 to 3. So 1 fraction comes out of photovoltaics and 3 out of wind. And if you translate it into powers, installed powers, then they are almost equal. So photovoltaics, 200 gigawatts, wind also 200 something gigawatts is what we have in the system. And if you ask now, what is this power in proportion with the average load or the peak load presently? So you see this little gray bar here, which is the load. And if we work this backward, you see the sum of rated powers from this calculation is 400 gigawatts, which hopefully never happens, because there's a little natural decorrelation. And probably what could happen in the system is some latent power of 320 gigawatts. Then we might introduce some peak clipping, some 70% of that. But then finally, you have still a factor between, and there the experts have a little discussion between, let's say, 3 and 5, between the present power consumption and the installed or necessary renewable installation, which is a factor of three times more, which can only be coped with if we invent new loads. So really we have to address the other sectors, not only for efficiency reasons, but we need this counter load. So what does this all mean to our question, should we expand rather on the decentral rooftop power plants, or should we do this on the right below picture, huge 10 megawatts and more photovoltaic plants? So let us make this little thought experiment that originally our electric system was devised such that we had the generation on the highest voltage level, and we were pumping down the power into the distribution and into the consumption. And if we normalize by 1 the total power that has to flow through the system, so through the high voltage or extra high voltage transformer, we pump 1, we pump another 1 down, and then we are ending up where the consumption starts. On the medium voltage level, there we consume 1/2 in the industry, and we pump down another 1/2 into the households, and the rest is consumed. Now imagine the completely adverse world where we do all the installation here. The photovoltaic should be representative of wind and photovoltaic. And let's take an Indian case where probably solar is a little stronger. And as I said, the factor between 3 and 5, now we are pumping 3.5, let's say, in this example, up in the system. So meaning to say that 1/2 could be consumed directly because they are rooftop installation. But then 3, the power of 3 has to go through the first transformer, which means that we have to enforce everything there 3 times, the transformer, the lines. But what we can do is, again, we will consume the other 1/2 here, and there's a rest of 2.5 that we have still to pump up, meaning to say enforcing the medium voltage transformer. And this is again transported up. Again there on the extra high voltage level, we have to enforce by a factor 2.5. And in brackets here are the original values of the original system. And then we can use that in the large load centers in the large cities as, let's say, the larger fraction of the renewable generation is in more rural areas. This looks like a lot of money and a lot of investment. And if you look at the title of my slide here, I'm saying economical optimization of PV integration without storage, because storage is an extra investment. So you have renewables and then plus storage, and everything you do with the storage has to pay back for itself. It's not for free. So let's try it. So we understand that the optimum lies there where we invest least. So now let's do it better. We do not do 3.5 the power at the low voltage level, but just 1. And we consume 1/2 again, and we pump up 1/2 again, which again is consumed on the medium voltage layer. Then there's room for having more photovoltaic installation on medium voltage. Let's say normalized again, 1 we produce here, which is pumped up. And another one is on the high voltage level. And then we have to pump 2 up, which was 1 before. So here we have the first occurrence of a additional investment on the grid. And we have room for another 1/2 here on the highest voltage level to go again into the load centers. So if you sum up here, you understand that on decentralized, if you want, so on the medium and low voltage, we have 1 and 1 is 2, and then another 1 and another 1/2 on the higher voltage there, meaning a ratio between 1.5, which we can call centralized or large plants, and 2.0 decentralized, which is much more away from this 95% we heard before, or 30% or so. And here again, this comparison, which shows that the effort, if we would do it all decentralized and all rooftop PV, would be much, much larger. So this is a kind of qualitative argument to show what has to be done in order to plan ahead. Yeah, I'd like to conclude with what I said in the beginning, that in the background of all of this is quantitative work. We are in the Institute somehow monitoring progress using these tools, and we promote somehow that we should do it with all people and countries partnering, like such a barometer, as we call it, where we fix such a target. Could do it for India here. I didn't calculate numbers for India. I'm very interested what the number would be that would you put here on the end of the bar where you see now target has been reached. And then we are monitoring whether we are on track. And we can see easily for Germany that we are not on track because at an installation rate of 2 or so gigawatts and multiplying that by a lifetime of 25 years, we see that we come out here in this wind question at 70 or 80 gigawatts, but we need some more than 200. Same with photovoltaics. Here you see the installation rate on the below curve, where we had this very interesting effect of ramping up quickly, and then we shrieked away from what was happening and ramped down again. Where actually we already reached the level which we think is necessary in the end. And yeah, this is what I said here. I compiled numbers which here I actually normalized. So for example, the installed renewable base with respect to the average load for Germany, we saw that in Thomas Ackermann's presentation already. I figured some 133%. Or the installation rate with respect to the target. So if we have 1.6% here, that means that we would reach the goal in 60 years. And I did it for other countries. And then you see if Korea is at 0.6%, it takes another 200 years to reach the energy system transformation. Or the US is presently probably overrunning Germany, but for all of these countries, including China, the pace is too slow, much too slow, I would say. For India, I put just X, because I rather want to stimulate this discussion and not come up with my numbers that I think are normative for India. So this is the end of my talk. I'm hoping that we could form such a network. We are presently building something that we call an energy transition hub, where we think we should do something like a harmonization of data structures so that you can use our data and feed that into your algorithms, and we can use your data to show it to fellow people at home. That's what the Indian situation is. And that we also, what I said in the beginning, harmonize on the mathematics, the methodology, the algorithms. Someone put that, Jacqueline showed us today calculations which are very similar to what we do in our institute, but would be interesting whether we also use the same kind of coding and then probably make a mix out of it that is a better solution of these tools. And then we could somehow annually, let's say, compare and say, where are you standing and where are you standing? Yeah, that's what I wanted to say. In just in one sentence, let's form a team. Thank you very much.